Okay, now I will talk about some of the devices that we use for measuring in the lab and some of the components. The first one is the galvanometer. And the galvanometer, it is a device that is going to actually detect very small currents. Okay, what's happening is um, you're going to find that when when we have like the current is going through the the wires, then it's gonna create a magnetic field, and then it's gonna create a torque, and that torque is gonna tend to push the pointer away from the zero, and when the spring is gonna try to make it towards the zero. Actually, many devices like ammeters and voltmeters, they have galvanometers inside. Actually, we can convert a galvanometer into a voltmeter. There is an experiment that we can do that. Okay. Um, Now, the second thing I want to talk about is ammeters you know, and voltmeters. Ammeters, they are really for measuring current. They have very low resistance because they're gonna be in the way. Okay, then they will not block the current. Like you can see here, there is a resistor, and the emitter is gonna be in the, you know, going through the circuit. Therefore, it shouldn't actually, it shouldn't block the current. Now we will say, like current through the resistor. But when we talk about voltmeters, on the other hand, voltmeters, they have they measure voltage or potential differences. They have usually very high, very high resistance, so that they will not have the current going through them, and then the voltage is not measured accurately. We usually say voltage across the resistor. And these are really devices that we use them frequently in labs. We can also use ammeters and voltmeters together to measure power and resistance. And this is really I would say, the arrangement. Now, also, there is another device that we might use, which is an ohmmeter. And ohmmeters actually, they have, we can calculate, uh, I actually measure ohmmeter. It is measuring, actually, measuring resistance. And of course, here it's, I will say, design. It contains a resistor that is variable. And this is like when we have that arrow here, means that this one is a variable. And to use the voltmeter, first we connect, um, you know, any resistor directly to Y and adjust R's until the meter reads zero, and that this is the way how really it is connecting. Okay, like here we have ports X, sorry, and Y. And then here, I will say we first connect X directly to Y and then adjust RS until that meter is reading 0, and it is like an ohmmeter, it is measuring resistance. Now we don't use maybe different devices. We use here what is called multimeter, and multimeters, especially the digital ones, are really very helpful because they give more accurate, and they measure because multi, they measure all the above. Now, one more thing I want you to know about, which is the potentiometer. The potentiometer, it is an instrument that can be used to measure the EMF of a source without drawing current from it. And actually, the potentiometer, it is just like this. Okay, this is the potentiometer. All right, now the most important now than this is the RC circuit. RC circuit, RC circuit means is gonna a circuit that have a resistor and a capacitor. Okay, and of course, no, for charging, we should have an EMF. Then the first one, it is when we are charging the capacitor. Then the circuit is gonna be, this is the capacitor, this is the resistor, and then this is the EMF. Okay, and therefore I will say we are going to have that capacitor is gonna start actually increasing its charge. Now the charge on the capacitor will actually grow exponentially, increases in this circuit, increases exponentially. With a time constant, we're gonna explain that. We call it tau, and tau it is RC. Now that is, as a function of time, is gonna be the capacitance times EMF 1 minus E minus T over RC. Or we can easily say this is the total or the final charge 1 minus E minus T over RC. Now, I will say if we want to graph this, this is going to be an exponential. This is time, and this is Q as a function of time. And usually we're going to have this type of graph, and that is really here where is the final charge. Now, I will say here, the charge exponentially is increasing till it reaches a value that is really the Q final. Okay, and we are going to also talk more about it when we talk about the, I will say, the other, we're gonna complete that, and then we're gonna talk about, um, discharging, and then we're going to solve problems. All right, and here for my circuit, we can start with that is EMF, and the current here is going to be 0, and then the Q will be 0. But then I will say, we will see that, the current and the charge on the capacitor is going to increase. Now, at some time when we close like the switch, and the current is gonna go, then I will say that, that the Q is gonna build up, and finally we will end up with this situation where we have, this is my EMF, and this is R, and this is the capacitor. All right, and like okay, then this is gonna have plus Q, and that one is gonna have negative Q, and that is after the switch, after having the switch closed. Okay, and we will see that the charge will increase, but the current in the circuit decreases. Now, this is if we want to find what is really the behavior of the current in the circuit, then we can draw this I versus time is going to start from the highest current I0, and then it will actually, what? It will decrease exponentially, and this is really E over R, E minus T over RC, or we can say this is I0 E minus T over RC. Now, on the other hand, okay, we're gonna see that also, if I will now open the switch, then I will say I will start the discharging of of the capacitor. We can say, okay, first that when I started, I have, of course, the current was I equals 0 across the resistor, because like that capacitor was reaching the full charge. And then this is Q0, and this is plus, this is negative, this is positive, and this is my capacitor. We're gonna find that the capacitor will start discharging through the resistor, and the magnitude of the current, here current decreases, and also Q decreases. This is when we discharge. We can, of course, have the graph for Q starts from Q0, and then it will have that kind of dependence. And I will say it will, the charge will decrease exponentially with a time constant again. Tau, that equals R times C. Now Q here is going to be the initial charge E minus T over RC. Then this is the dependence of Q on time. On the other hand, also, I can find like the current is gonna start, is the current is gonna start from, like I, a value, and then it's gonna decrease, okay? Then this is I0, and the current decreases exponentially as the capacitor discharges. The current here, it is negative because it is in the direction that is opposite to the one in the previous diagram. Here, I is going to be dq over dt, and therefore is going to be negative q0 over rc e minus t over rc, or we can say is going to be I0 e minus t over rc. Okay, then now I'm gonna stop here, and then I'm gonna move to, later to problems.